Alright, so good afternoon everyone. Today I'd like to introduce you to Chris Roman, who comes to us from the University of Rhode Island Graduate School of Oceanography. He earned his Bachelor's of Science in Mechanical Engineering from Virginia Tech and a Master's of Science in Mechanical Engineering from the University of California, San Diego. He did his PhD work at the Massachusetts Institute of Technology and Woods Hole Oceanographic Institution, and he specializes in marine robotics and seafloor mapping, where today he'll be discussing his work with stereo vision, high-frequency multi-beam sonar, and structured light imaging to create high-resolution maps.
All right. Well, it's good to be here. The funny thing is, Larry's been asking me to come up here to do a seminar for a year or two, and today at 3 o'clock he's giving a seminar at URI in our department. So it's like I waved to him up 495 somewhere around Boston as he was going the other way. But okay, so today's talk I'm going to cover some of the work going on in my lab, kind of connected to the Nautilus program, which you might know through Larry, which is an exploration program based at URI. We'll talk about that. And basically, sort of, this is a little bit of a kitchen sink talk. There's a theme. There might be a couple hard turns in there, but I'll try and keep you, let you know when they come up. But basically, we're covering these things. So some basic marine archaeology, marine geology, and then some work with a novel system we're using for habitat assessment. Oops. And before I go anywhere, I said these are 4 of my graduate students who probably did 90% of this work. So this is stuff they did, but I can take credit for. So what we're going to talk about today is sort of imaging techniques. We're working with 3 basic systems. So for 3D photographic reconstructions using high-resolution cameras, we're using high-frequency multi-beam sonars. So this would be, by high, I mean 1,375 kilohertz or 2.2 megahertz. So a little bit different than the shipboard sonars. Most you guys are probably much more familiar with than I am. And then a structured light laser imaging system. So this will be part of the talk. If you're not that familiar with what structured light imaging is, we'll talk about that. And that's what was used to make this map over here. This is an ancient amphora, so it's like the 5-gallon jug of the ancient world. It's about this big. And so we're doing, sort of trying to do in situ laser scanning on the seafloor of these artifacts. And things are looking up. Things are going pretty well. So the research directions are, where are we going with these techniques and what are we doing research-wise? So we're trying to get to high-resolution bathymetry maps, pushing centimeter or sub-centimeter resolution over areas that are tens to hundreds of meters on the side, up to, our ultimate goal is something on a square kilometer. If you could do a square kilometer, 1 centimeter resolution, you'd be talking about something. That's our ultimate goal here. We're looking at sensor fusion for acoustic and optical sensors, and then we'll talk about these novel imaging platforms. So the big part of the talk will be about the structured light and our new Lagrangian imaging float. And so the theme underlying all this, I'm not going to go into any of these details, but this is just something to keep in the back of your mind that all the plots you're going to see were created using this methodology, which is simultaneous collection of multiple sensors. So we like to do that. Looking for techniques that are applicable to archaeology, biology, geology. So we're looking for common denominator type techniques. We don't want to sort of do too much for any one thing, but it's come a solution that can help everybody. And all the plots are made processing with what's known in the robotics community as the SLAM framework, the simultaneous localization and mapping. So if you're into the robotics literature, you recognize this acronym. It's been a vogue topic in the last 10 years. And the idea basically is that we want to create mapping algorithms that can both utilize the mapping data, meaning your sonar or your images, and complement the navigation data. So for vehicles, we're talking about Doppler, depth sensors, gyros, that kind of stuff. And so we want to come up with one algorithmic framework that can use both of these pieces of information and make a map, rather than just use solely the navigation data. And the answer why is because typically when we start getting down to these sub-centimeter, centimeter level resolutions, your mapping sensors are pretty good and your navigation is pretty lousy. Right? Basically, it's a hard thing to know where you are underwater. So quickly, your navigation pollutes the sensor you just spent a lot of money buying, and you're going to combine that data with some cruddy navigation and get a cruddy map. So we end up using the SLAM framework to try and do one algorithm that can handle both. And the basic principle of it is you want to find areas on the seafloor. Perhaps there's a vehicle that swam around, made some maps. If you chunk them up in time, you can find places where you've seen the seafloor a couple of times, and you can take observations of a similar thing, try and register them, we call that, shift them together, create an actual navigation estimate, throw that into a filter, and beat out a better solution than you would get just using this stuff alone. So I'm not going to spend too much time on that. That's just sort of the undercurrent here. Our vehicle platform, this is what we use on the Nautilus program, and it's URI's main ROV asset. So it's a 4,000 meter rated ROV. It's got your sort of standard suite of navigation sensors. You have a nice north-seeking fiber optic gyro, pitch and roll, depth, velocity, with a Doppler that's mounted in the back, shoots down. We have two Dopplers at 1,200 kilohertz and a 600 kilohertz. So we can do surveys up to 25 meters off the seafloor before you run into problems with your Doppler not seeing the bottom. It's closed-loop control, so you can drive nice survey patterns. And this is pretty typical for doing surveys that are hundreds of meters on the side. So since it is an ROV, you got to follow it with the ship, and it gets tedious to do surveys more than a few hundred meters. So that's sort of why with this platform we're focusing on these really high-resolution surveys as opposed to big area surveys. Right? A little bit of the program in general. So it's called Nautilus because it's based on this boat called Nautilus. And so this is where Hercules at ROV lives. It's basically been campaigned 4 to 5 months a year. Exploration type program. Larry's on the board that helps advise this program. And we have a big public outreach end that goes with this. You see live video. This is a screenshot of our webpage. So you see live video from the seafloor, and we have a team of scientists always on board doing interesting stuff. Right now you can log on to this webpage, and the ship's, I think, about 100 miles off of Portugal, 150 miles off of Portugal right now, cruising around trying to find some vents. A little bit more details about the sensors themselves. So the vehicle platform, it's a Hercules ROV, everything's sort of mounted in the trunk here. We have a rigid rig that holds it all together. We try not to take it apart because calibration is a big issue. But we have a blue view sonar. So we've leased and now we purchased a blue view sonar. So at this 1350 and 2250 kilohertz, 90-degree swath width, and ranges, well, for this guy out to 30 meters and this guy out to about 10 meters. So you can't go too far at 22, at 2.2 megahertz. Our cameras are sort of standard HD type cameras, kind of a small field of view, strobe lit, but the benefit is these are 12-bit cameras, so you get a lot of dynamic range. That's pretty important. And then we have this thing we'll talk about for the structured light is a green laser sheet. So we packaged up a green laser pointer essentially with a prism in front of it that projects a sheet and draws a stripe on the seafloor. 532 nanometers, so it goes through water a lot better than a red one. And it's about 100 milliwatts. This guy is probably about 2. Right? So it's a pretty zippy laser. And then you put it through a fan, so it spreads the energy out, but it draws a nice crisp line on the seafloor. We'll see how we use that in a second. Most of our surveys sort of look like this. We drive around in some sort of regular pattern with the RV. It's closed-loop controlled, so this is pretty easy to do. It does constant altitude, so you say fly 2 meters off the seafloor. It drives a nice pattern, 2 meters off the seafloor. You make sure all your data overlaps. That's the big thing that we need to do to make sure that we can apply those SLAM registration methods, because the whole point of that is you got to see something twice to get any value out of this re-registration or looking at data and saying, I've been here before. Right? So we typically run something like 60% overlap between, well, 30 to 60% overlap across track, and we have images, can't quite see, but every little black square drawn on this plot is an image, and they tend to overlap something like 30% forward to back and left to right. Gives you a lot of redundancy. We do these surveys, the blistering 10 centimeters a second. And while we do that, we can shoot off the laser images at something like 15 hertz. So you can record photographs of that laser at 15 hertz. So you get a lot of data from that. Yeah, we'll see what we do with that in the processing. And so the first thing we were talking about is marine archaeology. And our motivation here is site documentation. So we've found a lot of shipwrecks in the last few years. I think we found 32 new ancient wrecks in the last 2 years, which is really unprecedented in the marine archaeology community. They're out there, you just have to look for them. When you have that many wrecks, it's a little bit different philosophy from the marine archaeology in the past, where you found wrecks so infrequently you treated every one like gold. We found 32 in 2 years. So our goal is now to go to these sites with high-resolution mapping tools and document them fairly quickly. So in a couple hours, we want to knock out a photomosaic, a bathymetry map that gives you enough shape, size, diagnostics that actually means something to archaeologists. Right? We can't invest a year in every site, right? Being that we can turn one up every couple hours. So we're trying to sort of get to these land archaeology standards underground, and you don't want to touch anything. As soon as you touch something, you're in a world of permitting and culture, and you just don't touch anything. That's the safest rule. So you want to be able to sort of document all this stuff in a forensic way remotely. But I'm not an archaeologist, and I can't keep any dates straight in my head, so why do I care about archaeology? Well, it turns out archaeology sites are really good diagnostic sites for learning and teasing errors and learning about your mapping techniques. Right? Why is because there's lots of detail. Right? So there's all kinds of fine scale detail. This is a composite image made of it's a section of a photomosaic made of about 15 images, I think. So, and these guys are something like this long. These are basically ancient. These are 800-year-old sewer pipes. And you can see the sort of male-female connections on them, like PVC pipes today. Somebody was building a town off of Bodrum, Turkey, and their ship went down. But the sites have lots of detail. You see lots of objects that are similar sized. So if you have a scale problem, you'll know it. Right? They look like pipes. So when you're done making a map, it should look like a pipe. Right? But it's still pretty natural looking. Right? So the texture information here is pretty consistent with what you would see if you went to a natural geologic site. So you're not putting cinder blocks on the seafloor, and that never kind of works out well, the ground truth here, because you put something totally not natural looking and then try and compare those results to a natural scene. It never really works out well. But these guys have a lot of nice information, but it's natural looking, and you can quickly see, although this picture looks really nice, you can highlight a few artifacts that pop out at you. This guy here has got a blending error. This guy here has also got a little warping blending error. This is doubled up. That's the same thing right there twice. This guy also has a little bit of blending error. It's hard to see that if you're just looking at coral reefs or rocks, right? So any rock looks like any other rock. But here you can see, offend all the geologists, but it's pretty hard to really ground truth yourself when you look at something you don't really know the answer to. Right? But here you know they should all look the same. You know what they should look like. You know they should be round. So it helps a lot in diagnosing these fine scale mapping errors. So we do a lot of this stuff. So we do photomosaics, bathymetry surveys, and then we can get some pretty decent detail. So this is an object that's about this big. This is now with this 2.2 megahertz sonar. And so we do more mosaics. This is a few hundred images. But you can I put this up here just to see the level of complexity in the scene. It's a pretty complex scene to try and resolve all that stuff, right? And so you want to be able to get measurements you can believe and put put a measuring tape on this stuff in the digital data product. So this was a sort of a conventional down-looking monocular photomosaic, but we're working also with stereo photomosaic. So you can take stereo images, meaning two cameras. With two cameras, you can reconstruct 3D point clouds, and you can make a 3D mosaic, essentially. So then you can honor the true shape and size of things. So here you can see the texture information, and here you can see this is the three-dimensional bathymetry backed out from the cameras alone. Right? So this is what it would look like for one image pair. So if you said two overlapping images, you can back out and make yourself pseudo 3D texture maps of these objects and maintain some pretty decent resolution. So this is one thing we're working on. Another example, so there's two other recs. And I say a lot of this work, the core mapping algorithm here that what produced these plots was our data collection and software that we're working with from the Australian Center for Field Robotics. The lead PI down there is Stefan Williams. And so we're collaborating with him quite a bit for this stereo mosaicing purpose. Another thing we're looking at now is how do you combine the stereo imagery and the acoustics. Right? So we're going to try and do all this mapping at one time. It often happens that there's no one tool that's the best thing on any given day. Or there's no one tool that's always the best, so to speak. So stereo is great. It preserves texture. You can really see what you're looking at, colors and shapes. But with water quality, it goes down pretty quickly. So you lose your ability to do the stereo 3D vision stuff pretty fast if the water gets turbid. And if low contrast scenes are a problem. So sometimes ancient pots covered in sediment, laying on sediment, is not a terribly interesting picture, right? So you don't have a lot of scene interest that makes it hard to do the vision processing to find interesting bits. So you look at the acoustics. So this is, can see right through schmutz in the water. Turbidity doesn't care. But it's not as great at complex edges or complex shapes, whereas there you'd really like to have this texture information and the ability of the camera to see crisp images. Right? So can you create a sort of hybridized views? This is work for one of my students, developing a sort of a seamless frame where you can produce a data product. So this little splotch of bathymetry here, these are ancient artifacts, was created with both vision and acoustics in a sort of a seamless way. So where there was very limited texture information, it brought the acoustic bathymetry data and made the shape. But where there was texture information, it used the stereo vision to produce the point cloud. And then it reprojected all the images back on top of itself. So you can preserve, you can't see right here, but there's like a sea urchin right there. So that's something you would pull out of the stereo imagery, but you'd have a hard time pulling that out of the acoustics. Right? But in the composite data product, when you're done, you have both. So that's something nice. So my student's working on a Markov random field and a Gaussian processing way of sort of looking at how to do this actually. So that was the archaeology bit, which those sites tend to be pretty small, 10 meters by 10 meters, maybe 20 meters by 10 meters, not that big. But we've been doing some marine geology work with the same techniques. So this is a place we were at for the last 3 years. I was there about a month and a half ago. So this is the Colombo volcano next to Santorini, Greece. Santorini, that's the corner of Santorini right there. There's an active vent field in the bottom of this guy. And this is one little section of it here. So this is a photomosaic. These are hydrothermal vents that are actually inactive, but there's some diffuse seafloor venting right here that's creating these biological mats. Right? So there's sort of wispy water coming out here, and this is sort of downhill. We're seeing sort of, there's almost like microchannel flow. Like you can see centimeter scale, sub-centimeter scale, river channels coming down. So there's some density-driven flow we're trying to get to the bottom of. And this high-resolution mapping is helping us figuring out the slope, what this fluid could be, what density could it be. And we're also interested in how often these things change. So this background picture was taken in 2010, and this was done 2 months ago. And you can see that it changed enough where this was not here the previous year, and this patch is a different shape than it was. So there is some time, 1 year time-varying change in this system, so we want to get back there. Once you have these high-resolution tools, you can really try and observe that. Right? So that was nice. This is that same area, and these are the vents now mapped with this 1350 kilohertz multi-beam sonar. So this area sort of is 50 meters-ish, and the whole resolution, mostly due to this slope, is something like 10 meters. But being able to do this surveys with this sonar and trying to create maps now that are sort of on the better than 5 centimeter accurate, down to sort of 2 centimeter accurate. So I think this was gridded at 2 centimeters. And trying to resolve these guys. And since we know in the area things are changing from this, we're interested, are these things, the bigger structures actually changing? If you want to say something about that, you're going to have to be at that centimeter scale to actually get some kind of observable change year to year. So this has been working pretty well. And then we did a bigger survey in the same area. That, what I just showed you is this patch, which is here. And this whole system is active. And this is actually where things are much more active down here. So we just did a bigger survey this year. And this is sort of pushing our mapping algorithm capability to try and do a survey now, which is 150 meters by 100 meters. Granted, it's not a square, but still, that's a much bigger survey than just this little box. So this is one thing we're working on now. This is what's complicating it. And this is what I think a lot of people here know better than I do. Venting and bubbles coming out of the seafloor that you stand out like a sore thumb in the multi-beam. So this whole area down here, most of these vents are active and spewing out both hot water and bubbles. The gas is mostly 99 point something % CO2. and the bubbles are coming out sort of sub-centimeter size. And when you do that big pattern, you go over stuff like this. You see places where there's a vent feature and lots of bubbles, huge swaths of bubbles, big bubble curtains coming out. So what we're interested in now, this data is only a month and a half old, so we're in the process now of trying to make this bathymetry map and separate out the inactive and active and what's bubbling, what's not bubbling. And there are also places where there was no vents and bubbling coming out of the seafloor, so we want to make a sort of comparison across the two at this sort of 10 centimeter or less scale. So that's we're sort of new in this game, so any advice would be appreciated. Okay, so that was the first bit, the sort of grand tour of what we're working on. Now the middle section here is talking about the structured light imaging system and how we're getting down to these fine scales. So if you don't know much about structured light imaging, this is sort of what it is. The basic principle is really straightforward, and it's actually been a sort of an industrial processes, land robotics technique for a long time. And it's, you take a laser, you put it through a prism so you get a sheet, you shine it on some objects, you take a picture of the stripe that laser would draw across those objects, and your picture would look like that. Okay? If you know something about the geometry between this camera and that laser, meaning at baseline, meters, angle, kind of physical things, you can then convert pixels in your image to real XYZ points. You can get yourself basically a multi-beam ping equivalently from the laser. Right? And so here's an example. This is what an image looks like on the seafloor. So there's your background image. Here's your laser line being drawn across some artifacts. And you're interested in the pixel coordinates of where that line is in the image. You can throw away everything else in the image. You don't care about it. You just want to know where those lines are in pixel coordinates. Okay? So a lot of people, and we're not the first people to think about this, but a lot of previous work has been done on sort of range or laser systems underwater, laser line scan systems, structured light projectors, triangulation systems. So this has sort of been around, but I think if we've done anything, we've basically taken the simplicity of just a simple camera and laser and sort of been able to get to what the core of these things do, but without a lot of the complexities. Right? Some of these larger systems that do time of flight, there's a lot of complicated signal processing has to go in there. These systems have always tended to be very expensive one-off things, but if you just reduce it down to the simple laser and the camera, you can get some pretty decent results for not a lot of money. So back to how it sort of works is you might start with your original image. So this is now, basically when you take the images raw, they just look like a line on a black background. If you take the log intensity of that, you can see a little more detail in it. So there's your line drawn across an object, and you want to just find the pixel coordinates of that line. So you can do some initial thresholding and chuck a lot of it away. Then you can do some sort of computer vision, morphological operators, filtering kind of stuff, chip away at a lot of the noise you might have here, and then sort of underneath this sort of blanket you've drawn, you can then go back and find the peak intensities and draw yourself a laser line. And you can get that down to sort of pixel level. Right? And you do this in a batch processing sense, so one of these laser surveys might generate 200,000 images. So you plow through them all in one shot. Right? If you're taking images for 15 hertz for an hour or two, there's a lot of images. So this took a little while to get this to work robustly and not be full of error. You guys know all about outliers and all that whole problem. The same thing applies. So the geometry works out, depending on how you arrange your camera and your laser, how they're separated, the angle of these two guys. You can create some basic relationship that says, DZ per pixel in terms of resolution. And typically right now we're sort of at this 5 millimeters per pixel. And then if you look at the actual, you zoom way into an image, and you see this is the laser line here. This is just individual rows, row 190, 191, 192. You can sort of start doing sub-pixel interpolation and get down to even better than your nominal 5 millimeters per pixel. Right? So now you're talking about millimeter level precision. The tricky bit about this, the part that's a drag, is calibrating it. So basically what you want is your image points over here and some 3D points over here. This thing in the middle is a basically linear operator that's called your projectivity, and you got to find this matrix. So you can get there a couple ways, through your camera calibration techniques, which are pretty standard, through some knowledge of your system, or some just basically derived camera calibrations where you look at points and image points. But this is not particularly easy. You can get close, but wringing out that last little bit of bias has proven to be hard. So I'll be a little careful with the words, precision and accuracy here, and that it's a high precision system, but accuracy is a question if you want to really tease out that last little bit of bias. So by bias, I mean your laser line is slightly warped, right? So you're sort of like your sound speed's off equivalent in multi-beam land, right? You got some dishing or some happy face, smiley face problem with your sonar. So we've been working on this, how to do this in a repeatable way. So you can do it with test tanks, and so we've been doing it in a test tank at home with a target and all this stuff. So here's your laser, here's a target. The checkerboard helps you learn something about your cameras and where the points are, and you draw your laser line and you try and beat out and solve for this thing. That's great in a tank, but if you've ever been to sea, you know things don't work well at sea. And sooner or later, you're going to have to unbolt the laser and the whole thing is going to go to hell. And you're going to have to do it again. Right? So you really want a way to do this at sea, so we're working on sort of in situ calibrations where we can use the stereo camera data, a piece of the seafloor, images of the laser line, where we find features specifically on the laser line, figure out where those features are in 3D space based on the camera geometry from the stereo, and then solve for the calibration using field data images. It's a little harder because you don't have like the known size of your checkerboards and things like that help you, but now you have a fighting chance if someone unbolts your laser and puts it back on the vehicle, because that'll change everything. So how does this compare with other things? So we've been looking at the laser and multi-beam data. So this is our laser data here over a single artifact, which is there. And this is the high-frequency multi-beam, and you can see the sort of how they differ. And the laser's pretty good at preserving edges. You can see the clear edge of that guy. Whereas, finite beam patterns for sonars, it's hard to get discontinuities and things like that. It's just an uphill battle, something you're always going to fight. So the laser is really particularly good in that sense. And you can even resolve this guy right here, which is this pot sherd. So it's something we fight about all the time on the ship. Archaeology, a piece of a broken pot is a sherd, not a shard. So you'll be corrected if you say shard in front of an archaeologist. But that thing's only about 1 centimeter thick, and you can see you're able to resolve the outline of it there, which is pretty good. If you zoom way in, the individual laser lines that you drew from each image, you can draw out like you're laser scanning, and you can clearly see the handles there. You can even see a growth, a bump there that was on the handle. Whereas when you zoom way in with the multi-beam, it's much harder to capture that level of detail, even at the 2.2 megahertz. And so with all the sensors, we've been trying to do comparative evaluations with gridded laser, gridded multi-beam, and then gridded stereo and see what modality captures things best, right? So the laser's probably the best for these ranges, and you get all the data points across the ping, across the beam. You don't have to worry about feature density and interestingness, which can really grind your stereo to a halt, or water turbidity is better here than here. The multi-beam will tend to work through turbid conditions after this fails, but there's really no one right solution. But by running all 3 systems at the same time, you have a fighting chance of trying to beat out the best map you can, even if you have to pick through multiple data sources. And so some of our results, small scale, are here. So here's our sewer pipes again, and you can resolve these. And I think this is gridded at 2 millimeters. Right? And you can even see in the laser data, 3D bathymetry land, you can see the even male-female ends of these pipes. That's a feature that's pretty small. Right? So now we're approaching something useful for archaeologists. Right? So that was our original goal. Right? And now we're trying to make this bigger. So this is a whole site now done with the laser data, where you can now zoom into any one of these artifacts and you can get that level of detail on it. Right? This is not that easy to do, mostly because registering, like I said before, that SLAM idea, where you have to take overlapping things and make them all jive and make them all look the same, isn't that easy to do if you have a little bit of calibration warping and you have a lot of detail in an individual pass. So if you just look at the raw data, you take away the background, you can see the kind of features you're left with, the rims of the amphora, the individual handles. Registering those things together when they're seen at different angles is not easy. So we're fighting this battle sort of in the weeds of, is it a calibration problem, is it an occlusion problem, trying to put the blame in, is it a navigation problem. It's proving to be difficult, but I think the results are fairly promising if we can sort of beef up the scale. We've also gone back now and done these same laser surveys over places like this vent field, and now the whole resolution on this map here is 50 centimeters. So you're really starting to resolve some details about these features and the surrounding seafloor around them. So now you can have you're back to your change detection thing. Can you image one of these sites and see how it's changing year to year if you can get down to this couple of centimeter or sub-centimeter resolution? Another thing that sort of just popped up we started looking into was we were doing our laser survey, you drive over one of these things, hot water spewing out. What happens to a laser shot through hot water? It refracts, right? So you get this mirage, and like, oh, crap. That's going to make the bathymetry maps go to hell. But you say, well, someone's problem is someone else's signal, right? So you say, well, wait a second. If the laser is refracting, I could use that and tell you where there's water coming out of the seafloor. So now we're working on a way to drive around with the laser and try and detect where it's nice and crisp and where it's not. And where it's not, it looks a little feathery and it's refracting. And you can say, there must be venting there. So if you've done geology cruises with an ROV and you drive around and you look for shimmering water and venting, you know it's tedious. It never feels terribly systematic because you're driving around looking for little wisps of fluid coming out of the seafloor. You might see it, depending on how it's lit, it's hard to see. Now this is a methodology where you can, back to your survey mow the lawn pattern, process it, and then make yourself a map that says that's where it's venting. So now you can get a distribution of venting. We're trying to figure out if we can sort of look at the temperature differentials and classify how rigorous it is even. We're thinking maybe the answer here is 2 lasers. You can look at the separation between them, how do you characterize refraction in sort of a principled way. So it's a sort of a freebie we got. We're trying to fight one battle. We realized, wait a second, we can use this for another thing. If you go over real sort of weak venting, it might look like that. Strong venting refracts the laser like crazy, and you can really see it. So you have a chance of actually classifying the magnitudes of the venting. And the last thing for that Colombo area, just to throw this in there, is the mosaicing that we've done up and down on the seafloor. We've also done up and down the walls of the caldera. So we took our Doppler and we spun it around on the front of the vehicle, shot it at the wall, and we're able to do surveys now on the vertical. And we were able to do those same mosaics and look at the layers of strata from the eruptions and the clasts that are in there. And we've been taking these guys and now doing processing that's not that different than the laser processing to try and extract out class size information and try and figure out what's the distribution of class and things like that. So this is just a little sort of freebie here that's connected to this whole Colombo area. So here's a hard turn in the talk, and present one more thing and then connect it back at the last minute. So in our lab, we've also been working on Lagrangian floats. So we started building these in 2008, sort of to be different than your standard Argos, Alice, Pallas, Apex floats for blue water oceanography that tend to work for years in 2,000 meters of water, the World Ocean Circulation Experiment. There's not a lot of floats or any floats that will work right out in the river or in coastal waters, right? Coastal waters, a lot more change in density. You need a higher capacity buoyancy changing system. The bathymetry is changing, so your chances of running into the bottom are pretty high. So we looked at a float that has an altimeter, shoots off the bottom so it could see where the bottom is, It's only 100 meters rated. Has a pretty big volume changing system in it. It has a piston that can drive water in and out. Right? So it can adjust its ballasting automatically. And sort of have it be a general Lagrangian instrument you can throw in the water, near shore and have it do similar things and track it. So things it can do that are useful for imaging are sort of two things. It can slide down and through the water and you can say go to 12 meters depth. It'll pull some water in and actively control its depth and drift to 12 meters if you ask it to. You can also say go down to 1.25 meters off the seafloor and stay there as it drifts away. So it can do that. So it uses the altimeter, measure how far the bottom is, and even if it's drifting and the water is getting deeper, it'll sink down and maintain this altitude. Right? You can also do a bunch of other profiling stuff, but we won't get into that just now. So, oops, flying that order there. So if you can do this constant altitude, we sort of had the idea, why don't we throw some cameras on this thing and take some pictures? Because constant altitude is the one thing you got to get right if you want decent pictures of the seafloor, right? So if you want constant scale, constant illumination from some strobe source, you better get the altitude right. So we have a camera system and a strobe we put on the float. You can throw it out, give it some desired altitude, and it'll drift along, right, and rattle off pictures. We run it with a tether most of the time, a little thin spectral line tether in a lobster float, so we know where it is. It's easy to go pick up. But there's no real reason you have to. It has Iridium communications built into it. But it's nice for getting basically low-cost imaging. Right? So started thinking about this a little more. I came to the realization that generally I think you can think about vehicle surveying in two ways. Right? Most of us think about vehicles, propellers, and motors, and their job is to get you from point A to point B. Right? You want to drive a survey, you got to go through the points, connect the dots. Knowing where point A and B are is a whole different game. Right? That's the underwater positioning navigation problem. Right? The first one, typically, requires propellers and motors. If you say, well, forget it, I'm just going to drift. So I can basically cross the complexity of my platform, my cost of my motors, my battery, my energy, all that stuff, throw it away. Say I'm just going to drift. All the cost and complexity associated with this collapses, and I still have problem too, but so does everybody else in the world, right? The question is, what's it worth to you, right? Depending on your job, what you're trying to survey, you might have to spend a lot of money to figure out where you are in the world. But if you're just going to do some basic reconnaissance somewhere, count a few scallops on George's Bank, does it matter what square meter of George's Bank you're on to that level? Maybe not, right? So the question is, if you're willing to sacrifice your ability to go exactly to a certain point A or B and just drift instead, you can reduce a lot of the complexity of the instrument and have a nice imaging platform that just cruises around. That's not. That's not part of the talk. But okay, we're going to go back. So we thought about this concept, and this slide I skipped. We started looking at sort of basic methodologies of surveying, everything from scuba, drop cams, tow sleds, ROVs, AUVs, and kind of tried to classify their costs in terms of ship requirements, personnel requirements, depth limit, navigation, data quality. It turns out the Lagrangian platform has a fairly desirable set of characteristics depending on your end goal, right? And you got to think, it's not just the cost of your vehicle, it's the cost of how many people you need to run it, it's the cost of the boat and the A-frame to put it over, you're going to have to sit there for a while, what are you going to do with the data when you get back? If you start looking at the total cost package, you can see you can simplify your life. And Lagrangian imaging concept seems to make sense for a lot of applications. So an example is you can throw it off the ship, say here, drift around this altitude, 2 meters, it'll drift down, it changed depth right there, and then came home while I was taking pictures. This was a perfectly calm, windless day, and it can hold altitude to within 5 centimeters or something. Sort of a nasty day where my grad student and I were getting beat up in a 19-foot boat in sort of meter-sized waves, and we had that surface tether to it. The float had to fight a lot more, but was still able to maintain a nominally constant altitude above the seafloor to within tens of centimeters. So why it's doing this is taking pictures, and you can string those all together using the same mosaicing software we're working on for the archaeology business. Right? So this example, we went out, set it to 1.3 meters, pictures every 3 seconds, and my student and I in a 19-foot boat got several multi-kilometer long surveys done in an afternoon. I thought that was pretty decent, and the images look really good, and that's sort of when you're 1 meter off the seafloor, you can get some pretty high resolution images. And you're probably not going to want to run a lot of torpedo-shaped AUVs 1 meter off the seafloor, right? So you actually have a decent chance of getting higher res, closer images with the Lagrangian concept. And so far, we really haven't run into any terrain it hasn't been able to handle. And I don't have any great in situ video to prove this, but I just think about whitewater rafting, and that water tends to flow around stuff, not into stuff. Right? When you go rafting, you rarely hit a rock. You go around a lot of rocks, but you don't hit that many of them. Right? So I think basically this was in a bouldery area where there were meter-sized boulders, and you're only 1 meter off the seafloor, but the water tends to pull you around those kind of objects. So we don't really have a high collision risk, even at this 1 meter off the seafloor. Nets are another story, but everybody has that problem. So now we can go back and think about our same stereo vision technique. So now 1 meter off the seafloor, we can create these stereo vision patches and get roughness now, which is the total vertical relief here is about 7 centimeters. Right? So now you're getting size information for these rocks. Go back, use the same sort of size classification stuff we're using for the wall at Colombo, and now you're talking about doing size sorting, size classification at 1 meter off the seafloor, which has been pretty good.
This is from your Lagrangian vector?
Yep, this is from the Lagrangian float. And you can also do this, which is get near bottom current measurements, right? So you're taking images and they overlap. You know something about your altitude, you know something about your timing, you can figure out how fast you're drifting. So you get sort of a freebie, basically a drift current speed, which is hard to measure otherwise in a sort of continuous sense, right? Near bottom current measurements in the bottom boundary layer are a pain. ADCPs looking down have blanking range problems. Tripods looking up are typically above that height. So this gives you a nice near bottom current measurement. And you can even go down to 80 centimeters off the bottom, come up to 1 meter, come up to ½ meter, and then look 1.5 meters and look at the difference and actually try and resolve the bottom boundary layer. So we've been playing with that a little bit. You basically can do these current measurements by taking a bunch of sequential images and finding stuff in one image that's in the other image. And if you can find all these matching features, and you have stereo, you have scale, so you can get a real meters per second answer. And you can also use that meters per second answer to help better your GPS estimate of where the float was. Right? So we're also working on a navigation scheme that could use your GPS here, use your bottom current information here derived optically, and your GPS here to actually come up with a fairly believable drift track of where you think you are on the seafloor. The camera also has a compass in it, so you can get vorticity. So you can actually watch the rotation rate of the thing as it's floating and spinning around too. There's no real reason it wants to spin on its own. So any rotation rate, it's a pretty, it looks like a lot of these paddle wheel drifters and paddle wheel vorticity sensors people stick out there. It's got these big arms on it, so it's grabbed the seawater. So I'd say it's a reasonably believable measurement of rotation of the flow. So I think we're at the end here. And so the last idea here is that's clever, but it's not really an AUV. So what are you going to do with it? We see opportunities here, fast reconnaissance surveys. You want to just show what's in some area before you bring out the big guns of a much more expensive vehicle and ship. You want to just throw something in and see what's there. Not a bad option for a simple Lagrangian platform to give you some decent data. Then in management areas, right? We have a lot of management areas we're interested in across the, out in the ocean, perpetually undersampled for funding reasons and a lot of other things, right? But if you can collapse asset costs down, you have a chance of doing something and helping yourself in areas that you're going to repeat survey. And we like this idea. in parallel with other activities. So we've been working now on the Rhode Island SAMP project. It's a big wind farm assessment project in Rhode Island. Every state in New England has a wind farm assessment project now. So we've gone out and had large areas side scanned, and we want to get ground truth on some of the side scans and some of the transitional regions from one water classification type to another. So we've gone out with the float, chucked it in the water, got drifts across these transects while the ship is off doing grabs and doing other stuff. It's been pretty flexible platform to use. And then working on a proposal now that sort of beefs this up, which is the idea of if you have an area you want to survey persistently, you go out in year 1 with the big guns and do an AUV survey, beat it to death, right? Year 2 through N, you want to know, is it worth going back out there with the big guns again? That's where you can do Lagrangian imaging, right? Something that's cheap. You have a chance now of registering these new images to this data set if you can find intersections, and instead of doing your image registration problem within a data set, you do it between data sets, right? So now you're thinking more of a database strategy, right, where you have a high-cost asset and a low-cost asset and try and work out the navigation complexities between the two. I think that's an interesting direction for this research. So I think that's it. Went a lot of places, but hopefully there's some questions. And I just say this work is sponsored by the usual suspects. Our collaboration with the Australian Center for Field Robotics, and then the Nautilus program is funded by the Institute for Exploration, Ocean Exploration Trust, and the University of Rhode Island. That's what I had.
Two sort of related questions. One, with your stereo system and the laser, have you considered dropping just a calibration target into the water? You can do that with land-based robots when they're driving past a target. And you've got a ship there. So like the first stereo images that we did in the 90s were looking at propellers and ships and things like that. So you could put something on the hull of your ship or drop something over the side. Mm-hmm. And related to that, you're also looking in the stereo at boring bottoms. Why not structure your light that you're using to illuminate the scene and use the classic thing that we use in the lab when we don't have any texture, which is add light texture onto your scene so that you can get better stereo matches?
Yeah, so both good points. The first one is we have tried targets on the seafloor, and it just never seems to work out that great in that deep with the RV, getting a big, there's a lot of practical, just with getting a big enough target on the seafloor that's got some 3D shape to it. The problem you do, if you want to get a good calibration, it's best to have the target occupy the whole image at some point and give you lots of, the problem actually is mathematically degenerate if you only have one plane your target's on. So kind of on an RV, you're stuck with the cameras looking down. You can't twist and move them sort of like this. You can spin them, but that's about it. So it's nice to have a target that's not flat on the seafloor, but at an angle, and then drive around and try and do it. It's just we have tried it. It's just practically we've always gotten better results using more angles and targets and better field of view in the lab. For the second point, yeah, you can do the structured light like you do in the lab. The question is just getting a marine structured light setup going, and so we've basically always been using the conventional strobes that don't project the pattern.
For structured lights are lights that are broken.
Lights that are okay. Yeah.
Seriously, damaged lights are great.
Okay, we've seen a little bit of. We basically actually do some processing to try and remove light field artifacts to get synthetically create more uniform lighting than we're actually projecting, but we haven't yet tried to actually use that for calibration purposes or for.
It works pretty well.
Yeah, we'll have to look into that.
You were talking about your blue view multibeam, and you were seeing gas heats, and then you're talking about your laser system, and you were seeing the hot seats.
Yeah.
I was wondering if you were seeing those with the multibeam as well. It seems like at that frequency they should stand out.
You do a little. Well, go back there. You do a little bit, but trying to separate that out from the bottom is. Did I pass it?
That's gas there.
That's all gas, but this is a combination of gas and water. So you're seeing sort of everything in one shot there. And we haven't seen a signal of the hot water in the multibeam that we've been able to successfully pull out better than other things. Because you sort of have the problem with the hot water is coming out where the relief is really high. So you sort of have a lot of things going on there. If you saw the hot water out of a nice flat spot in the seafloor where you're pretty confident in your range image, that'd be fine. But it tends to come out of much more muddled 3D structure, so it's hard to separate the structure from the water. And the temperature gradient is so severe that the water really exists just within a boundary layer close to the structure. The refraction dissipates quite quickly away from it.
So is it literally like that?
Yeah, I mean, it's close. I mean, that's the thing, because you get a temperature quenching is really extreme. So you don't tend to see the thermal anomalies this far away are sub-degree. I mean, they're really small. It's a really steep curve within that 10 centimeters, so it's hard to get it away from the structure and the bottom. So,
but that sub-degree anomaly you are picking up with the lasers? Higher above?
that's what we're trying to learn, actually. We're not 100% sure. So we have a bunch of test data from like 3 different sites where we went and temperature probed some area, and then we laser mapped it for refraction purposes. So we're looking at, we know the temperature differentials were about this, and we're trying to go back and correlate that to the image and say, well, okay, could we detect it or not? So that's sort of a work in progress. Yeah. You had a question?
You said you were having problems calibrating your camera. Are you using like a Leica or Zeiss, like photogrammetry kind of camera, or are you going on the cheap like a SLR?
It's a machine vision camera with a 9mm lens in it. So it's not a rectilinear lens or like a photogrammetry lens. Right now you do have issues underwater with the lens, air, glass, water problem, where that fundamentally violates the pinhole camera model, which basically 90% of your calibration procedures use. There's ways to get around that, but they're all sufficiently unpleasant that we haven't really dove into any one right now. So we're just also really trying to get a handle on where the errors are. With the camera calibration, it's like you get like all of a sudden the laser resolution is incredible, but it also brought all these other problems to light. So we're sort of working our way through them now.
How small is the system, or can the system be made?
Pretty small. The laser itself is probably that big. It's 90% housing. By the time you put in a 6,000 meter housing, it's gets pretty big. But I mean, it's literally this little thing. It takes 4 watts. So I mean, if you're in shallow water, you can make that thing a little PVC housing. I mean, there's nothing special about it. I would be a little bit concerned about the rigidity of it. You want things to move, but still, it's very scalable and it's not that expensive. Yep.
Great. You're doing a lot of good stuff there. The very last slide, the last line, I think you said bathymetric particle filtering. And I don't know what that means.
Oh, so yeah, so one of the registration techniques we're thinking about for improving our float nav is you throw the float out, it drifts around, you want to know where it went. If you have a bathymetry map of an area, I'm sorry. Yeah, it's right there. So particle filtering is a pretty standard robotics technique. And the basic idea is it's a stochastic idea where you say, I have a platform that could be here. It's going to drift some increment of time. And I'm just going to simulate the randomness, which I expect to be in the system. So I'm going to create fictitious samples of this thing. I'm going to get 100 possibilities of where it could have gone. I'm going to then take a real bathymetry measurement with my float. And I'm going to take a bathymetry map that I have in a computer and say, what would any of these 100 floats have seen if it was there? And I compare the two. Some of them are going to be consistent, and some are not. So you take the ones that aren't, and you throw them away, and you take your survivors of those 100, and you do that again, right? And then you take another measurement. So you can basically beat out a likelihood track of where you've been if you have a single line of depth measurements and a bathymetry map of the area you're working in. So it's a pretty common technique that's been done for underwater. Yeah, it's been around for a while now. So this is our idea. If you have the GPS, you have the optical velocity, you have a bathymetry map, you have it, composite here, you can probably beat out a fairly decent navigation without having to spend the money on the sensors in the front end. You can do it all algorithmically in the back end, especially in an area like a management area where you're going to have a good bathymetry map because it's your management area, right? So you're going to already know something about the area. Yeah. I can talk to you more about that after if you're curious. Yeah, it's,
With the blue view multibeam, you show the water column imagery. Can you log that, or is it just logging detection?
you get everything. You can log everything. Yeah, the files are big, but there's a SDK to pull them out in MATLAB or whatever you want to do. So that's the thing. So now we have all the water column data, so we're trying to go through and process out the water column data to separate the bubbles from the bottom.
Yeah.
So you can, yeah, it's all free. You can do whatever you want with it.
Okay. What's the endurance on the Gaussian floats? What's limiting?
The camera system now is a limiting factor because it's a PC104 with a network switch. The whole thing, it's like 10 watts or 15 watts, so it's not terribly power efficient. With the float now, you can talk about 8 to 10 hours with the camera running. Without the camera and a CTD and a fluorometer and other stuff on it, you're 24 hours, 36 hours, something like that. We haven't done a great, we're at iteration 1.1, so we haven't done a great power audit to low powerize everything. And then the float also tends to jitter the piston a lot. It's sort of a little spastic. We could calm down the control algorithm a little bit and not waste as much energy going, with trying to drive our line here.
Okay. Did you see any? There's a pressure sensor on there.
Yeah.
Do you see any surface wave effects?
You do,
Kind
actually.
of driving it to overcompensate.
You do see surface wave effects, and this is something that I know Larry and Art had gone through this with maybe you were involved in that. Yeah, I got on this data right here. I was looking at it. I was looking at the control signals for where the motor was going. And I see this periodicity. It's like 6 seconds, 7 seconds. What the hell is that? And then I sort of touched my hand. I was like, wait a second. So I went back to the local weather VUZM3, the NOAA tower there, and looked at the wave spectrum for that day. It was like 6 seconds. Like, there you go. And so calculating, that's obviously, and it was only like a couple centimeter fluctuation at depth, but it was enough that the control system was just going like this the whole time. So how to actually get rid of that in real time versus post-processing are two different sort of animals. But yeah.
Thanks.
And you're getting spatial coordinates from the laser system. Are you assuming a constant in the index of refraction in the water column, or is that something that you allow to vary?
Yeah, so there we're assuming it's constant. So we try and calibrate in water and just leave the calibration alone. So we haven't tried to go to correlate the index of refraction with like water temperature or that venting. So that's what you're getting at.
So you do it once in calibration, and then you assume that those values are constant over your project site?
Yeah, so like that's the benefit. If you can do the in situ calibration before you do the laser survey, you can take a bunch of stereo images and laser images before you start. Use that in situ calibration and then do your survey and use those calibration values for that survey. But if you picked up and went from the Black Sea to the Aegean, you should probably do it again because there your index refraction might be a little off. It doesn't change a heck of a lot, but enough that you probably should think about it. So that's what you're getting at, I guess.
You said that Nautilus had found 32
Something
ancient
like that.
wrecks or something like that
Yeah.
in the last couple of years. How many of those have you guys had a chance to do a lot of this high-res multi-beam and some of the imaging that
We have a whole catalog, yeah. We've tried to do it on every one, but inevitably things happen. So you go to one wreck and you found it on the side scan sonar, you get there and it's like pea soup visibility. So you can't do any visual stuff, you just take a multi-beam map. So visibility is still a problem, with the stereo. The laser cuts through the stereo better, but it doesn't give you photo quality images. So pretty much for every one of those 32 wrecks, we have some combination of these three techniques done. If we get to a wreck and it's crystal clear water and we have the time, and no one's yelling to go someplace else, and the ROV works, and it's not lunch, all the possible things that can be a stick in the spokes. We generally have them. So the one thing actually we're working on also, and I didn't show it here, is if you look at the intensity of the laser line that comes back from those images, and you just now make a plot of intensity, you actually can get like a monochrome photograph, and you actually can color code this in terms of intensity and get sort of a monochrome photo out of that. So that's actually been quite cool. We're not sure exactly what to do with that just now, but
As a related thing, do you do any radiometric calibration? I guess either of the laser or of the imagery that you collect?
not really. I mean, we know what the wattage of the laser is, and we know we can see it. We fool around with depending on our altitude. We've been fooling around with our camera exposures to try and see it but not blur it, kind of. But we haven't really tried to calibrate it so we can say something definitive about the scattering.
Or about the reflectance?
Yeah. No, we haven't. You can see changes in it, but we can't really say much about that in a quantitative sense. But there's enough there you can actually see it, and you can kind of get this funny pseudo photograph out of it.
All right, well, thank you very much.
Sure.